Assalamu alaikum. Welcome back to week number 3. We are discussing chapter number 8, switching in networks. I'm your teacher Hassan Shah. Last week we discussed the circuit switch networks. This week we will see how packet switch networks send data. Therefore, first we will talk about the packet switching networks, and then we will talk about how we can use the two different types of packet switch networks to transfer data from one point to another. So let's start packet switching. In data communication, the thing which is very important is to send message from one end to another. If a message is going to pass through a packet switch networks, it needs to be divided into packets, fixed or variable sizes. So packet switching is all about sending packets. The size of packet is determined by the network and the governing protocol. We talked this thing about in chapter number 1 and chapter number 2 as well. The different protocols have different size of packets. So in this technology, packet switch networks, we'll be using protocol dependent packets. In packet switching, there is no resource allocation for packets. So there will be four things that we'll be looking at. This means that there is no reservation of bandwidth on the link. So the links are independent. They have different multiple bandwidths which can be considered while transferring the data. And there is no scheduled processing time for each packet. Resources are allocated on demand. And lastly, the allocation is done on a first come first come first serve basis. When a switch receives a packet, no matter what the source or destination is, the packet must wait if there are another packets being processed. So queuing is there. As with other systems in daily life, this lack of reservation may create delay. So delays are there if we are not reserving the ports in a switch or a link in a switch. We can have two types of packet switching networks, datagram and virtual circuit networks. So first, let's talk about datagram networks. In datagram network, each packet is treated independently. That means that each of the packet that needs to be transmitted from point A to point Z, each packet is treated independently. Even if the packet is a part of multi-packet transmission, the network treats it as though it exists alone. Packets in an approach are referred to as datagrams. So these packets are called datagrams. Datagram switch is normally done at a network layer. When we are doing it on network layer, we need to use routers. You can see here the switch element is a router here because we are showing you that this is layer 3 network. We briefly discussed datagram networks here as a comparison with circuit switch and virtual circuit switch networks. We will talk these things later in other chapters. The figure here shows the datagram approach is used to deliver 4 packets from station A to station X. So 1, 2, 3 and 4 packets are being transferred. The switches in a datagram network are traditionally referred to as routers. So this switching element are routers because we are using third layer protocols. That is why we use different symbols for switching in the figure. So later on we'll see these switching elements will be changed. Instead of routers, we'll be probably using some switch as well later. In this example, 4 packets or datagrams belong to the same message, but may travel different paths to reach the destination. So they may take different paths. So they may take this path, this central path, or the path at the bottom. This is because the link may be involved in carrying packets from other sources and do not have the necessary bandwidth available to carry the packets from A to X. So the thing is like they are dependent upon the bandwidth. So the packet may take this path, the middle path, or the path at the bottom. This is because availability of the bandwidth and the resource. This approach can cause datagrams of a transmission to arrive at a destination out of order with different delays between the packets. So here we can see they are out of order. The out of order is just because of different bandwidths. So the packet has taken this path and it has a larger bandwidth, so it probably reach here faster than the packet that has taken the other path which has low bandwidths, probably take more delay, and that is the reason they will arrive at destination with out of order. In most protocols, it is the responsibility of the upper layer protocol to reorder the datagrams or ask for lost datagram because before passing them on to the application. So it is quite possible that the packets in transit may get discarded or probably get lost. We'll talk about this part, lost. What do we mean by lost later in next chapter, inshallah. So the packet, if doesn't arrive to destination, the destination may ask for the packet to be resent. The datagram networks are sometimes referred to as connectionless networks, so we are not making any connection over here. No connections being made. The packets arrive in the network, takes any route to the destination. So this is called connectionless. The earlier when we discussed about circuit switch networks, if you remember, we discussed about the first part in which we are setting up the path. That was basically connection oriented. These are connectionless. So we can see in datagram networks there is no setup and tear down phases. Each packet is treated the same by a switch regardless of its source or destination. So now let's talk about how this packet finds its way to the destination. Let's talk about the addressing a little bit. So we have routing tables for that. If there are no setup or tear down phases, how the packets routed to the destination in a datagram networks? Well, in this type of network, each switch has a routing table which is based on the destination addresses. So you can see here we have destination addresses against each port. So we have 3 ports or 4 ports here with this router, and when the packet arrives, let's suppose from port number 1, the router has the destinations where the router can forward the datagram. It has port number 2, 3 and 4, and it has different destinations. The routing table are dynamic and update periodically. So how these tables are being built? They are dynamic. We haven't talked about anything about routers, but definitely we'll talk about routers later in chapters. The routers say hello to other routers which are on the other side, and whether the router is off or on, it sends them the information, and that's how they build their table, and that's why they are called dynamic. The destination addresses and the corresponding forwarding output ports are recorded in the table. This is different from the tables of a circuit switch networks, in which each entry is created when the setup phase is complete and deleted when the tear down phases is over. So circuit switching is different than datagram switch. Now let's talk about destination addresses. Every packet in a datagram network carries a header that contains, among other information, the destination address. So remember, if we talked about the datagram network have a payload and an address, which is called destination address. When the switch receives the packet, this destination address is examined. The routing table is consulted to find the corresponding port through which the packet should be forwarded. This address, unlike the address in a virtual circuit networks, which we'll discussing later, remains the same during the entire journey of the packet. So in virtual circuits, probably what we will see is that the address change, but in datagram networks, when a packet arrives at the switch, its destination address remains the same. If you remember, we discussed that part in chapter number 2, where the assignment number 1 was probably given to understand the change of addresses, where we talked about routing addresses and MAC addresses. Let's talk about the efficiency in datagram networks. The efficiency of datagram network is better than the circuit switch networks. Resources allocated only when there are packets to be transferred. So we are not doing any setup phase or tear down phase, just transferring the data. If a source sends the packets and there is a delay of a few minutes before another packet can be sent, the resources can be reallocated during these minutes for other packets from other sources. So if there's a delays, if there are larger delays over here, we can change the destination and find or we can say we can reallocate the resources which are available, higher bandwidths, to transfer data. or this delay will help other devices to send packet during this time. So let's talk about delay. There may be a greater delay in a datagram network than virtual circuit networks, as there is no teardown and set of phases. Each packet may experience a wait at a switch. So you need to see there's a delay here shown. There's a delay of we can say it's maybe probably a queuing delay or maybe a processing delay. In addition, since not all packets in a message necessarily travel through the same switch, the delay is not uniform. So this we can say we have showed you here that the packet is traveling through these two routers, but the possibility is there may be other paths that a datagram may take. So this is not actually real, but this is ideal condition where we're talking about the packets are all passing through these two routers, and there is a specific constant delay that we can see here, waiting time. A delay is not uniform for the packets of a message. We can see a datagram network for one packet. If a one packet is passing, it has to wait some time, get processed, get queued, and move to another router, get processed, and then firstly it will be queued, then processed, and it will forward to the destination. So now let's talk about the packet that travels through two switches and the delays. So here we can say there are three transmission times, that is 3t, three propagation delays, that is a slope that you can see is called 3 tau, and two waiting times, w1 and w2. We ignore the processing time in each switch. The total delay can be represented as you can see at the bottom, that 3t plus 3 tau plus w1 and w2. That is all for the datagram networks. Let's move on and let's talk about virtual circuit networks. Well, a virtual circuit network is a cross. That means it's a hybrid between circuit switch networks and diagram networks. That means it has some of the properties of circuit switch, where we have the setup phases and teardown phases, and it has the property of datagram as well, in which we'll be sending packets. So as a circuit switch network, there are setup and teardown phases in addition to data transfer phase. Resources can be allocated during the setup phase. So what we're doing is during setup, we'll be allocating the resources and we'll be connecting them or holding them till we transfer all the transmission or the packets. As a datagram network, data are packet sized and each packet carries an address in the header we discussed earlier. However, the address in the header has local jurisdictions. We will talk about virtual circuit networks addressing, which is global and local later. However, the address in the header has local jurisdiction. The local jurisdiction, when we talk about local jurisdiction, it means it defines what the next switch should be and the channel on which the packet is being carried, not end-to-end jurisdiction. So local is just about within the routers or the switches itself. The reader may ask how the intermediate switches know where to send the packet if there is no final destination address carried by a packet. So what to do here? The answer will be clear when we discuss virtual circuit identifiers in the next section, and we will talk about global addressing. As a circuit switch networks, all packets follow the same path established during a connection. So what the link that we have established in a setup phase, all packets will follow the same route. A virtual circuit network is normally implemented on a data link layer. So we will show you that the elements of the switching has been changed, the diagram has been changed, and they are now you can see something like a switch. And switch is of a secondary device, and that is data link layer, while a circuit switch is basically implemented on physical layer, and datagrams are usually on network layer. Let's move on. Check out the diagram here. This is the virtual circuit network, and you can see these are the switching elements now. The switching elements pictures has been changed to a switch, which is second layer device other than third layer, because we know that virtual circuits basically work on second layer. The network has switches that allow traffic from source to destination. A source or destination can be a computer, packet switch, bridge, or any other device that connects other networks. So what we are discussing over here is like we are getting a wider view where you are not actually transmitting a data within a LAN, but actually you are transmitting data globally, like from Pakistan to probably America or Google. So how we do the addressing? In virtual circuit networks, two types of addresses are involved, global and local. We just talked about local addressing previously. This time we will only talk about global addressing. A source or destination need to have a global address, an address that can be unique in the scope of the network or internationally if the network is part of international network. So it has to be unique. However, we will see that a global address in virtual circuit network is used only to create virtual circuit identifiers. So what is virtual circuit has? Virtual circuit identifiers as a address. Let's talk about first virtual circuit identifiers. They are called VCI, virtual circuit identifiers. A VCI, like a global address, is a small number that has only switch scope. That means it understands only the switches that are part of the network. It is used by a frame between two switches. So what is it? They communicate, the switches communicate with each other using some frames. When a frame arrives at a switch, it has a VCI. When it leaves, it has a different VCI. What it means is that frames arrive at a switch, it has a certain type of VCI, but when it leaves, it has a different VCI. The figure, if you can see, shows how the VCI and datagram changes from one switch to another. Note that VCI does not need to be large number, since each switch can use its own unique set of VCI. So each switch has its own VCIs. So every switch has its own VCI that it can uh, add to a packet when it enters the switch and it leaves the switch. So the picture over here shows you that the data that have arrived with the address, it enters the switch. When it leaves the switch, it has different address. So let's talk about the three phases of how we can transfer data in a virtual circuit networks. The three phases, we can see that there's a setup phase, there's a tear down phase, and lastly there's a transmission of the frames. As a circuit switch network, which we talked about previously, well, we can see that virtual circuit is part of is a kind of circuit switch network as well. A source and destination need to go through three phases. In the setup phase, the source and destination use their global addresses to help switches make table entries for the connection. So what we'll do is like we'll send, if we want to make a transmission from here to Google, we're using a virtual circuit network. What we need to do is like we need to set up the path from Pakistan to Google, and we'll send a frame, and that frame will pass through all the networks in between Pakistan and Google, and they will create a path, and all the packets later will follow the same route and reach the Google. So in the setup phase, the source and destination use their global addresses to help switches to make table entries for the connection. In the teardown phase, the source and destination inform the switch. So both the source and destination informs the switches to delete the corresponding entries. Data transfer occur between these two phases. We first discuss the data transfer phase, which is more straightforward. Then we'll talk about the setup and the teardown phases. So let's talk about first the data transfer phase. To transmit a frame from a source to its destination, all switches need to have a table entry for the virtual circuit. So this is over here, what we can see is the table entries. So the data comes in, it has a specific type of VCI. The table already been built, that if this VCI with like 14 or 77 comes in, what it needs to be done, they have to forward to port number 3 by giving it another VCI, that is 22, and if it's VCI 77, we need to forward to port number 2 and we will give it a VCI 41. That's what it's shown here in a diagram as well. The table is in its simplest form, has 4 columns. This means that the switch holds 4 pieces of information for each circuit switch that is already set up. So the setup we haven't discussed about the setup. The setup will discuss how these entries are how these entries are built, which we haven't discussed yet. We are just discussing how we can transfer data from one part to another. So for the moment, we assume that each switch has a table with entries for all active virtual circuits. So the frames are at port number 1 with the VCI 14 and leaves the table, the switch table looks for it in a table and find port number 1 and VCI 14. When it is found, the switch knows to change the VCI to 22 and send out to frame from port number 3. Similarly, it shows that the frame from source A reaches destination B and how its VCI changes during the trip. So you see here, the data, if we are sending a data with the VCI 14 reaches the switch looks up the table, changes the VCI and forward to the next switch. The next switch, when receive the packet from port number 1 VCI 66, forwards the packet out from port number 2, changes the VCI, and then the last switch, when it receives, looks up the table, forward the port to the end station. Next, we'll talk about setup phase for virtual circuit. In the setup phase, a switch creates an entry for a virtual circuit. So the thing is like to create an entry. For example, suppose station A wants to send data to station B. 2 steps are required: the setup request and the acknowledgement request. So what we'll do is like we'll send a packet that will probably set up the phase, set up the route from A to B, and what we'll do is like the B will send an acknowledgement frame back to station A to create a link. So we can see here in the setup phase, when we are transmitting the data to station number B, this entry is not there. All 3 entries are there. Port 1 VCI 14 will reach, so port 3 will forward it to switch number 2. So what we're doing here is we don't know whether switch number 2 is available, it's busy, or it has so much load of transmission, so we don't know. So what we'll do is like we can send this packet and it will determine the direction or the connection to the next switch, and once it will reaches the last one, then it will the last station will send an acknowledgement frame, and the acknowledgement frame will actually, what we'll do is like fill up this last part of the table. So let's see how this thing is work. We have 2 pictures, this picture and the next one. So let's talk about the setup phase. The setup request frame is sent from the source to the destination. So number 1, source A sends a setup frame to switch number 1. You can see here, this is the switch number 1. Switch 1 receives the setup request frame. It knows that the frame is going from A to B, goes out through port number 3. How the switch has obtained this information is a point covered in future chapters. We'll talk about this later in chapters. The switch in the setup phase acts as a packet switch. It has a routing table which is different from the switching table. For the moment, assume that it knows the output port. So we are not discussing about how this thing is actually works, but we are just assuming that these things are there. The switch creates an entry in its table for this virtual circuit, but it is only able to fill 3 of the 4 columns. The switch assigns the incoming port 1 and choose an available incoming VCI 14 and the outgoing port 3. It does not yet know the outgoing VCI, which will be found during the acknowledgement setup. The switch then forwards the frame through port number 3 to port number 2. Switch 2 receives the packet or the frame. The same events happen here at switch number 1. 3 columns of the table are completed in this case. Outgoing incoming port was 1, VCI was 66, and outgoing port 2. Switch 3 receives the packet. Again 3 columns are completed. The incoming was port number 2 with VCI 22 and outgoing was port number 3. Our destination was B. Receives a set of frame, and if it is already receiving frames from A, it assigns a VCI to the incoming frame and that comes from A. In this case 77. This VCI lets the destination know that the frame comes from A and not from other sources. So now to fill up this last part of the table, let's talk about acknowledgement. A special frame called the acknowledgement frame completes the entries in the switching table as shown in the figure. You can see this thing is being filled up here. The destination sends the acknowledgement to switch number 3. The acknowledgement carries the global source and destination address, so the switch knows which entry in the table is to be completed. The frame also carries VCI 77, chosen by the destination as an incoming VCI for frames from station A. Switch 3 uses the VCI to complete the outgoing VCI column in this entry. Note the 77 is the incoming VCI for destination B, but the outgoing VCI is for switch number 3. Switch 3 sends the information, acknowledgement, to switch number 2 that contains the incoming VCI in the table chosen in the previous step. Switch number 2 uses this as the outgoing VCI in the table. Switch number 2 sends an acknowledgement frame to switch number 1 containing the incoming VCI in the table chosen in the previous step. Switch 1 uses this as the outgoing VCI in the table. Finally, switch 1 sends an acknowledgement to source number A that contains its incoming VCI in the table chosen in the previous step. So this one. The source uses this as the outgoing VCI for the data frames to be sent to destination B. So that's how this whole table completes. Now let's talk about efficiency. In this phase, now let's talk about teardown phase. In this phase, source A, after sending all the frame to B, sends a special frame called a teardown request. Destination B responds with the teardown confirmation frame. All switches delete the corresponding entries from the tables. So it's free. Let's talk about the efficiency in virtual circuit networks. As I said before, resource reservation in a virtual circuit network can be made during the setup and can be on demand during data transfer phase. In the first case, the delay for each packet is the same. In the second case, each packet may encounter different delays. There is one big advantage in a virtual circuit network even if resource allocation is on demand. The source can check the availability of the resource without actually reserving it. Consider a family that wants to dine in a restaurant. All the restaurant may not accept reservations. The family can call and find out the waiting time. This can save the family time and effort. Alright guys, let's talk about the delays in virtual circuits. In a virtual circuit network, there is one time delay for setup and one time delay for tear down. If resources are allocated during the setup phase, there is no wait time for individual packets. So we already set up the path. Figure shows that the delay for a packet travels through two switches in a virtual circuit. This is ideal condition. The packet is traveling through two switches. Uh, there are three transmission time, that is 3t, three propagation times, 3 tau, just like packet switching. But here we can see another thing which is called data transfer depicts by the slope lines. A setup delay includes transmission and propagation in two directions, and a teardown delay which includes transmission and propagation in one direction. We ignore the processing time in each switch, so the total we can see is 3 tau, 3t plus setup delay and a teardown delay. So what we can see is that virtual circuits are basically more applicable in WANs. We'll talk about WANs later in chapters. Thank you very much for watching the lecture. Next time we'll talk about structure of the switch, how this switch actually works and what's inside the switch. Thank you very much. Take care. Bye.